And Val is an emeritus professor of physics at Colorado College, living on San Juan Island and participating in Orcasound.net.
So, do you see my screen, Jasper?
Yep, I do.
Great. So I'm going to give a short report on work I've been working on for a couple of years. Real-time detection and classification of underwater soundscape signals for the killer whale calls. So short version, convolutional autoencoder 1 year on, or more small, even smaller, computing on the edge. This is work that Scott and I have been working on for a couple of years. We have Orca Sound, lots of things going on there. You'll hear a little bit more about it in a few minutes, but we have our Raspberry Pis, and we have at one end, and we have our web app at the other, and many, many things with many people helping in between. We have Orca for AI telling us that there are calls, and gave me a false positive last night. So false positives are an issue that we all have to fight with. We're moving into image analysis. So we have an underwater streaming video cam down near Seattle, and we have a system at our house that looks for ships and boats. And this particular photo shows that they found one sinking. That's the Aleutian Isle that sank near our house just a few hundred meters away in August. But I'm here to talk about autoencoders, and the motivation for an autoencoder in the AI world here is feature extraction. I've built this software that takes a spectrogram, puts it into the input to a neural network, makes the neural network get small, 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 and then gets big, big, big. And in the middle, we call that the encoding layer. I don't know if my mouse is on the screen or not, but it's here by this H. And the idea behind this is that we can extract features from the spectrogram that are common enough that we can use those features to rebuild the spectrogram on the other end. So this is a non-tutored training system where the input's a spectrogram, the output's a spectrogram, and if you can get them to match, somehow you did it through this little minimal layer. So that's kind of what we're working on. This is what the current convolutional autoencoder looks like. A lot of detail there, which you probably don't care about. But the main point is that it takes a 256 by 256 spectrogram, sorry, hit the wrong button, and turns it into an encoding that's only 2048 power spectral densities, or 32 times smaller, and then takes that 32 times smaller thing and builds it back up to its original thing and sees if it can manage to do it. And so now here's kind of the game plan for this talk. Over on the left, we have all the things that Scott worked so hard on that are actually working. It's really small on the screen, but it's really big, actually. We're going to calculate lots of normalized spectrograms. We're going to develop an autoencoder, get some encodings, build a binary classifier, and play with that. That's kind of what this talk's about. So first, normalized spectrograms. I've made this pitch at a few other meridian-oriented talks, and I'll do it again. That spectrograms are fundamentally grayscale. We like to look at them in color, but it doesn't really add any information that an AI can use. And so I spend my time normalizing my spectrograms. So the middle one is normalized to plus minus 2 standard deviations from the mean of the power spectral density, and then I square it, in this case, and get this much more contrasty spectrogram where I've squared the normalized spectrogram. And that works because if you square numbers near 1, they stay near 1. If you square numbers not so near 1, they move farther away. So that brightens up the spectral features in the spectrogram. So we normalize them, and then we train the autoencoder. I talked about this a year ago. So this is an input. This is what the output looks like, an input and output. It does an amazing job. I won't talk about that anymore because that's sort of old news. But here's what the encoding layer looks like. Starting at the bottom, we put in an input spectrogram. We get these 8 blocks in the middle. That's the encoding layer, and then we can use those to reconstruct the spectrogram, and that's in the lower right. So again, what comes in, comes out, that tells us that the encoding layer is working. And I've been pushing the encoding layer towards sparseness, and that in this case ran one of the weights in this particular feature down to 0, and hence and I only have 7 of these things. But I can reconstruct the output from only 1/32 of the input data. So now we've kind of calculated lots of spectrograms. We've developed an autoencoder. We've now calculated lots of encodings. And what I've been working on these last few months is trying to figure out what to do with them. And here I'm going to show a very small convolutional neural network that tries to classify these features, these encodings into call or no call. And then we'll come down to the bottom of this figure, and we're working toward Val's holy grail, which is real-time detections on edge devices, little things like the Jetson Nano and the Maxim 78,000. Those are the two I happen to have sitting right behind me. So here's a very simple classifier. The input to it are the encodings from the 1/32 of the inputs normalized spectrograms. And so the input is 2048, let's call them power spectral densities or feature components. And the output is a floating point number between 0 and 1. And if I run that on a data set where I've got some where I've got some labeled calls, I can see how it works. So up here in the upper right, I run it on a small set of calls. Looking at Harold's numbers there, he's up in the 40,000. I'm in the 4,000. There's a difference between one guy sitting on an island and another guy sitting with an entire agency behind him. But on my small number of labeled calls, I'm doing pretty well with a recall of 94% and a precision of 99%. So I was amazed I could do that in such a simple little network. And you might say, well, it's all overfitted. It's just memorized your 4,000 calls, but that doesn't seem to be the case, because below here I have a small data set, 500 or 550 calls that were randomly pulled out from the original set of labeled calls, and run the little CNN on that set, and I do pretty well. There's still there are now some more false negatives, about 3 times as many false negatives, and maybe 6 times as many false positives, but there's still a small fraction of the total. So it's doing remarkably well, with a recall of 87% and precision of about 94. So I'm feeling pretty amazed that this is how well this simple little classifier works. Now, what can I do with it? Well, here's where I have to back up and tell you a little bit about how I labeled these calls. So over on the far right of this screen is what Audacity looks like. If you use it as a labeling tool, you can draw boxes around spectrograms, and it will record the start times, the stop time, the max frequency, and the min frequency, and then you can use those as your labels, which is, as I understand it, the standard way to label these sorts of things. But I'm too old to do all that, and I wouldn't quite know what to do with it. So what I did was much, much simpler. Maybe it's not a good idea, but I'm pretty enthused about it. And that is, I used Audacity just to label that there is a call. So this little insert to the left of the Audacity panel, where my mouse is, which you may or may not be able to see, is where I've clicked on this call and say, hey, there's a call somewhere around here. And that to me then is a labeled call. I just know that at 27080, there is a call. Now, how can I use that to train a neural network? I have to have some examples of no calls. Background. You can go to background from a different file where you know there aren't any calls, but that's a hazardous process, as Kagel learned a couple of years ago, when the AI learned just to figure out which file the data was coming from, and if it knew that, it knew whether there was a call in it or not. So you really need to get background that has the same acoustic structure as the world, the soundscape within which the calls are delivered. So what I've done is written a little algorithm that goes through these couple hours of test data, and looks for times when we're pretty far away from a call. And I make the assumption that if we're more than 7 seconds before a call or after a call, that this will be a background sample. And if you're close to a call, I say, well, I don't know. I'm not too sure, because there are weaker calls, and calls tend to come in clumps and groups. So staying away from calls is a better assumption as background than saying everything doesn't have a click on it is a call. So I end up then with the data set used for training that little neural network you just saw of 7,000 or so calls. It has about 3,110, exactly 3,110 clicks that I did. And the algorithm found about 2,400 samples within those WAV files that are far enough away from the calls that we can call them background, and the rest of it are too close to call, so they just get labeled as not labeled. Now, I used those labels, the calls and the backgrounds, to train the neural network. And now I can use the neural network to take a look at the non-labeled and see what it thinks of them. So if I define a call as a prediction greater than 0.9 and a background as a prediction of less than 0.1, then I can run my little CNN you just saw and see what it does. And over here on the right is what it did. So it found that 60% of the 7,000 spectrograms that make up this tiny data set, 60% of those are sort of labelable by the CNN. That is to say, have numbers, predictions above 0.9, so that would make them likely to be a call, or below 0.1 likely to be background. And that's 60%. That's not all of them. You couldn't decide everything, but if my predictions were random between 0 and 1, I would expect this number to be 20%. That is, that which is above 0.9 and below 0.1, and 60%. So actually, it's pretty amazing. The number that pass these thresholds we're talking about and disagree with Audacity are about 36. So of these 3,000 calls that I labeled, this algorithm thinks that 36 of them could be suspect, where I labeled something that wasn't a call, or I guess, I labeled something that wasn't a call. So I need to look at those, but that's still only about 1% of the Audacity labels that need to be checked to see what was Val doing when he clicked on that stuff, and what is the algorithm doing. And out of the end of this process, I get some more labels. So I get about 769 labels. So with that, I have built a larger label set. And the plan going forward, that's my time. I'm still got a minute or two. My plan going forward, where's the mouse, is to keep iterating this structure, this idea. So to review, we gather the data, we store it, we normalize, we auto-encode, we get lots of encodings, we build a CNN, we use it to classify calls, we add some more WAV files, haven't done that. We loop this around a few times. I've been putting check marks here. Notice a very small check mark. I really only touched this. And the Holy Grail still is off in the future. I've been trying to implement this autoencoder, or the encoder section of the autoencoder, and the CNN in the Jetson Nano. And I've got the WAV parts working well. It can read the files and do the A to D, but I'm stuck in the TensorFlow problems. And the Jetson Nano is built by NVIDIA to use the NVIDIA GPU, and all of this should be seamless, but when you're down in the weeds doing computer programs, there seem to be seams everywhere that we stumble over. So that is still the work to do, is to make this, iterate this and get many more labeled calls and check them, and then get this the CNN and the encoder section of the autoencoder to run in the Jetson Nano. I want to thank all the many people that have been helping on these projects. Orca Sound is a very large group of volunteers, a few paid people for special projects now and then, but mostly it's people that come to us through our hackathons, come to us through the web, and show up as volunteers. We've had students through this Google Summer of Code for the last 3 years. Microsoft has been helping us with AI and alerting me that there might be whales at my house, but there weren't this morning when they said so. And all of what we're trying to do is open data and open software. And I put a link to our GitHub. My GitHub over here is Autoencoder GitHub. And if you were to go to GitHub, Orca Sound, Orca Autoencoder, you'll find my code, and you can laugh at it or look at it or make it work better. And our theory is that the orcas need our help. We can't fix the salmon. That's really hard. Maybe DFO can fix the salmon, but I can't. And I can't clean up the environment, but I can work on the harassment that underwater noise may play in the lives of the orcas. And that's something we all can do. And if we have data that can help in that, we have labeled data to help the automatic processing we're all trying to do. We need to share those data and we need to share those labels. It will advance the science, and advancing the science will help save the orcas, and they're terribly endangered, as everybody on this Zoom knows. So I think that's kind of where I come to an end.
Great, thank you so much for that great talk, Val. We have time for a few questions. I ask that people please post your questions in the chat box and I will read them out, and any extra questions can of course be asked in the breakout rooms later. So we have one question so far. It is, how long in total were the recordings you used for training?
Well, that's about 3 hours of a reasonable pass by about one year ago. We've got many more hours and many pass-bys, but for me it was a question of, well, how much do I want to label in order to play with these very small systems? And so I thought, well, if I label 3,000 or 4,000 calls, that should be enough to get started. And then my goal has been and continues to be to use the algorithm to generate more labels, so I can just sit back and relax and sleep. I'm 80 years old, got to get my afternoon nap and let the darn thing find more calls and maybe check a few. So it's a very small training set.
How do you decide how small to make your autoencoder layer?
I tried to make it as small as I could. So I tried many different things, and we could go through the autoencoder, which took me a year to fiddle around. And I'm not totally happy with this one because I got that one feature set that's blank, which seems like, oh, that's pretty good. I should be able to make the whole work smaller so that I'm not, so that I'm using all of the neurons that are available there. So I think it can be compressed further. What surprised me in doing this over the last year or two is just how well the I should have had the previous screen on, shouldn't I? Anyway, how well the autoencoder does. It sort of surprises me.